Okay, hello everyone, welcome back. So now let's talk about some different units of pressure. So there's also Pascal and then millipascal or kilopascal. So a Pascal, 1 ATM is equal to about 101,325 pascals. And if we divide that by kilopascals or turn that to kilopascals, we're dividing by 1,000. So that will be 101.325 or megapascal, which is 1 million, is the prefix for a million of something. And so that's going to be 0.101325 megapascals. But usually for pressures, we use pascals or kilopascals. Megapascals is usually a bit too big. Okay. All right. Now let's start talking about the gas laws. So Boyles Law. Boyle's law states that the pressure and volume of a gas at constant temperature is inversely related. So what this means is, if you kind of think about this in terms of tire, right? The volume there, if you decrease the volume of the tire, as you try to put more air into the smaller volume, the pressure is going to increase until a point where it bursts. So that's why you have a set limit on your tires of the pressure it can maintain, because if it gets too high, it's going to ruin your tire. Okay, so we use the equation P1 times V1 equals P2 times V2. So for this equality to be constant, if we increase the pressure, so say pressure here is 0.1 atm and the volume is 1 liter, okay, and we increase the pressure tenfold to 10, sorry, not 10, but 1 atmosphere. Okay, so for the volume to, for this equality to stay constant, or to be how we say, for this equality, for this equation to remain true on both sides, the volume will have to decrease to maintain, because the product of this side is 0.1, right? 0.1. So for this to remain the same, the volume would have to decrease tenfold. So V2 equals 0.1 liters. Okay? So if we increase the pressure by 10, that means the volume should have decreased by 10fold. So V2 equals 0.1 liters. Okay? All right. So we can actually depict the Boyle's law using these two graphics here. So you see here, as we so the initial level of mercury is right here. So this is the initial volume. So you see here that the mercury has been displaced by so the initial mercury that was in here has been displaced because we've added more mercury into the apparatus there. So what that does is that increases the pressure due to gravity, right? So the pressure in the tube now is going to increase. So, and since the tube has a known volume, we see here that this volume right here, it has displaced the volume. It has displaced the mercury, which now the volume is now decreased. So we see here the volume is decreased, and then the pressure increases because we've added more mercury. That means more mercury. Then you're going to feel a bigger pressure due to gravity. And we see here, so these units are inches of mercury. So they, instead of millimeters, they measure inches instead. We see here as the pressure goes up, right? As the pressure is increasing, so increasing pressure. So we see here increasing pressure, and we see the volume here is decreasing. So we're going down in volume. The volume is decreasing. Okay, and we see the ratio of our P pressure times volume is it's pretty much if we think of like kind of an average, it's an average about it's roughly the same, give or take a few values up and down, right? So the product is essentially constant. It's not changing much at all. Okay. So for this relationship, we have to keep the number of moles and temperature constant because that number of moles or particles affects the pressure. So the more molecules of something, the more pressure you exert. And then we have to keep temperature constant because that both affects the volume of gas occupied, and that also affects the volume. The pressure. So increase in temperature usually means increase in pressure. That's why on the hot days, you have to kind of deflate your tires a bit because the increase in temperature will cause the particles in the air in your tire to expand, to move faster, and that will cause an increase in pressure. So you don't want to increase the pressure too much that your tire kind of implodes. So it's important that on hot days we kind of take that into account. So temperature will affect both volume and pressure, and moles will affect the volume. But we'll go more into that as we discuss our gas laws here. Okay? So that's Boyles Law. So Boyles Law relates pressure to volume. They are inversely proportional. Just think about like the air pressure inside a room. If it's a larger room, you don't feel the pressure of the air as much because the air is more widely distributed throughout the room. But if you're like in a cubicle and you're blasting the fan, you're going to feel much more air pressure, and you're going to feel, if it's an AC unit, right, the room's going to get much colder faster. So there's going to be much more pressure of the air throughout the cubicle. Okay? All right. So now let's go on to the next concept here. Okay. So now let's talk about Amonton's or Gay-Lussac's law. So historically speaking, this law it's not really clear who this relation belongs to because they kind of both studied it during their lifetimes. But I'll get to the second person, Gay-Lussac's law, in a bit. He did something else, but mainly this is Amonton's law. So what this states is that the pressure and temperature of a gas are directly proportional. So if we think about it, right? If we heat a gas, so when you boil water, right, the gas particles are moving very fast as steam. So increasing the temperature of a gas is going to increase the speed of which the gas moves. So we say they're directly proportional. So this is why, the car manufacturer, they recommend adjusting your pressure of your tires before you start on a long trip, because the flexing of the tire as you drive will raise the temperature of the air in the tire. So that has to do with, kinetic energy. It will transfer to the air from the tire. The energy will transfer from the tire to the air, and that will cause the pressure to increase. Okay? So we could demonstrate this equation saying that the change in pressure, P1 over P2, we should also see the same kind of change in temperature. But what I mean by change is that the ratio of the pressures will equal the ratios of the two temperatures. So this is considering we keep everything else constant, the number of gas particles and the volume. Okay, and we can rearrange it like this. P1 over T1 equals P2 over T2. And if you cross multiply, you can get this equation on the right from the equation on the left. Okay, so here are some demonstrations of, this is what we call Amonton's law. Okay, so here's the apparatus that is used. So it's a pressure gauge connected to a metal sphere of constant volume. It's metal because if it was any other material, the material could expand and it can increase the volume. So we don't want to do that. So we immerse this in water at different temperatures. Okay. And then we see there's the dependence of this on this table here. The higher the temperature, the higher the pressure. So 100 degrees, the pressure is 18 psi, and then at below zero, it's around 10.8 or 11. And we can see here we can extrapolate this point to a direct relationship. So this looks very similar to what we did in lab the previous week, graphing our data for two variables and see the relationship between both. The relationship between the two variables. So this is how we extrapolate actually absolute zero. So absolute zero is when the pressure of a gas approaches zero, and that's approximately at negative 270 degrees, or an absolute zero, negative 270 degrees Celsius. So that's where no kinetic energy of a gas is present, and we say that that's where the energy of that's the lowest temperature we can achieve, because if there's no kinetic energy, there is no temperature, right? Because kinetic energy is the average, temperature is the average kinetic energy of your system, so of whatever you're measuring. So if you're measuring temperature of an ice bath or of water, it's the average kinetic energy of your water molecules or any other sample. Okay, so when you take the temperature of anything, it has to do with the kinetic energy or the energy from the motions of the particles that are moving. Okay, so that is pressure and temperature. Okay, one of the more important laws here is relating temperature to volume, Charles' law. Okay, so the volume and temperature of a gas are proportional. And this kind of explains how a hot air balloon works in the sky, right? So as you increase the temperature, you're expanding the volume. So you're increasing air in your balloon, and it'll help you float or fly. Okay? As gas is heated, it will expand, and that's how volume increases. So that's how... So that's pretty much how inflatable things work. You put air pressure in it, maybe heat it to expand. So gases like to expand when heated. They contract or compress when cooled, and etc. Okay, so the setup, how we do this experiment is, so this experiment is very, very tricky. What you do is, so you submerge a flask in an ice bath. The gas sample in the flask here, it'll be cooled, okay? And then to determine the volume, to determine that the temperature influences the gas, the volume it occupies, we have this little syringe here, and then what happens is this plunger can be moved. So how we detect this volume and temperature relationship is we take the gas out of the ice bath, warm it up, and then as the gas expands, the gas will expand from the flask and will slowly push up the position of the syringe, meaning it occupies some volume. So it's displacing the syringe out of the plunger, the plunger out of the syringe, or the piston of the syringe. So indicating that it's trying to occupy volume. Okay, so that's how you would kind of measure this relationship or kind of record this information in the lab. All right, so here's some data here, raw data here. So at temperature, we see the volume is 107, and then as we slowly increases, it's going to occupy more volume. Now, this also depends on the sample of gas. So the more sample you have, the more volume will occupy. So ideally, if you had a larger sample, you would occupy more volume based on, a ratio of um, say you measured a small sample and a large sample, the volume occupied can be calculated by a ratio of the moles. But in this case, we do not change the number of moles because that can affect volume. So in this experiment, moles are constant and pressure is constant. So in this case, the pressure is not being changed at all. It's being the same because we have a closed system. The pressure will not change because the volume, there's a exit way for the gas to escape, and that's through the syringe and piston there. So it moves the piston up because the gas is trying to escape, increasing the volume it occupies, thereby when you warm up the gas, the increase in pressure is negated by the increase in volume, so there's no net change in the pressure. Okay. So that's Charles' law. All right. Now let's get to the last two laws here. Gay-Lussac's law. So what he did, he tried to study the volumes of gases consumed or produced in chemical reactions, and he saw something very interesting. So in this reaction between hydrogen and oxygen to form water, he found that around 200 parts by volume of hydrogen were consumed for every 100 parts by volume of oxygen. So this pretty much means if I took 2 liters of hydrogen was required to react with 1 liter of oxygen to form, in this case, 2 moles of water, 2 liters of water. Okay, so it looks like it reacts in a volume ratio of 2:1. Well, that sounds vaguely similar to the chemical equation where we say 2 moles of hydrogen reacts with 1 mole of oxygen to give us 2 moles of hydrogen gas. So it seems like these ratio the chemical reactions, it seems to also be related to volumes in terms of gases when we talk about gases. So this law quickly became known as Gay-Lussac's law, which states the ratio of volumes of gases consumed or produced in a chemical reaction is equal to the ratio of whole numbers or a ratio of whole simple numbers at constant temperature and pressure. So it had kind of a direct relationship to stoichiometry, and this kind of connected to the next law I'm going to talk about. Okay, so now we'll go to Avogadro's law. So Avogadro is the same guy who discovered the mole, or conceptualized the mole. So a very important man. He sought to explain this observation from Lussac by stating that, equal volumes of different gases contain the same number of particles. So that's why he stated that the reason why you can think of this in chemical reactions is because in the balanced chemical reaction, there's 2 moles of hydrogen and 1 mole of oxygen. So the fact that you can use this in ratio of volumes is that they must contain the same number of particles. So like 2 liters of hydrogen must contain the same number of particles as like 2 grams of hydrogen atoms, right? Or hydrogen molecules, okay? So, but more generally speaking, he was trying to say that the volume of a gas is proportional to the number of particles in a gas. And he went out and did some experiments which proved that equal volumes of different gases at the same temperature and pressure, they had the same number of particles. And we're going to see that in this setup right here. So here's this simple setup. It doesn't look very sophisticated, but it does the job. So what happens is he has this plunger, or this syringe, So he's going to, so this syringe can be moved. So so in the experiments, he put in enough gas where the syringe read 50 milliliters. Then he capped the syringe to lock it in place so it can no longer be moved. And he capped the tip of the syringe so no gas can escape. So first he weighed the empty syringe and then filled it up with 50 milliliters of gas of different elements, and then reweighed and found a mass of 50 milliliters of said gas. And these were his results. So you see here, 50 mils of hydrogen was very small, 5 milligrams, nitrogen 50 milligrams, oxygen 60 milligrams, carbon dioxide about 90 milligrams. This is butane, around 111 milligrams, and then this is dichloromethane, and that's 228 milligrams. And you see here, if we compare the molecular weight and then times it by Avogadro's number, the number of molecules in each case is on average the same. So you see here, all those numbers, that's very good data. So it this proved that the number of molecules in a gas is proportional to the volume. So if you have more volume of a gas, you're going to have more molecules. And this is kind of how we can think about representing chemical reactions, not only in terms of moles or molecules, but also volumes. And we're talking about gases. Okay. So in general, we can say that moles, or number of particles is proportional to volume. And then we can use this relationship. If we have a set of conditions of mole and volume, we can find either the moles at a different volume or the volume when the number of moles has been increased or decreased. Okay. So let's stop there, and I'll pick up finishing this discussion on Avogadro's law, and then we'll talk about doing some problems. Okay, so see you in the next video.